Okay, so you have today's document open. It says balloon fuse demonstration. You see up at the top there, it shows a circuit. It's a drawing, not a circuit diagram. We could do this as a diagram, but it's an actual sketch showing a battery. It has 5 different wires, a light bulb, a switch over to the left, and then we have this balloon structure that we're going to put into it. Okay, so I'm going to switch over and share my screen, and I'm going to show you my circuit. I actually have it here, and I'm going to build it with you. And I want you to think about the electrons and things like that as I'm building this. Okay, so we have our source of electrons right here. I have some alligator clipped conductive wires that are insulating outside covers on them. The electrons are going to flow out of the battery. They will, if I connect this into a closed loop, they will light the light bulb. There's a little bit of a delay, I know, with using this camera. I'm sorry about that. Okay, so evidence that this circuit is complete is the light bulb is on. That means the electrons are flowing through the wires. They're flowing through the light bulb. And if I open the system, that flow of electrons stops because it has to be, they are pushed out of one side and pulled back in. We need that, both the push and the pull to make the electrons flow. The reason a light bulb does what it does and lights up is that there's a little tiny wire in there called a filament, and the electrons have to go through that wire. They're going from a much larger wire into a smaller wire, which means there's a lot of friction. Friction causes heat. We get a lot of heat, and you know if you touch a light bulb, it feels hot, and it glows because of that friction as well. Okay, the heat is something that we don't want. This light bulb and some light bulbs are designed to produce light. So the heat is waste. A light bulb that produces a lot of heat when it's supposed to be producing light is inefficient. It's more efficient to have less heat and more light, or the same amount of light. Okay, so we have a source of electrons. This is a chemical that is, so we're storing energy chemically here. The chemical energy becomes electrical energy once we connect it all up into closed circuit. The electrical energy converts to heat and light. That's called an energy conversion. Okay, then it goes back to the electricity and back to the battery. Got a little lag problem there. Sorry about that. Okay, so in this closed circuit, it's fairly safe because we have a resistor. We have a load that is using the electrons. That slows the electrons down on their path. Okay, so I'm going to stop right there. I want you to think, what did we notice in the simulation or on your desk when you were actually using the same equipment? What happens if our circuit does not have a load? What happens, so you can type it into the chat, what happens if the circuit doesn't have a load on it? What happens to the electrons as they're going around the path? So I'm going to go back over to Big Blue Button. I want you to type in the chat.
The electrons would just travel back to the battery and it would catch the battery on fire.
Okay, yes. It could catch the battery on fire. Why? What happens to the electrons if they're not going through a load?
There's nothing stopping them.
There's not that there's not stopped. It's that there's nothing slowing them down. We want them to flow. We just don't want them to flow unresisted. They go really, really fast, and that causes a lot of friction and heat and possibly a fire. And a lot of times in the simulation when you did that, the battery started on fire. But in reality, I think on the whole circuit, it gets really hot. And some of you felt that with the wires, the alligator clips got hot. The light bulb, things get hot in there. And we don't, if you think about in your walls of your house, the walls of your house are built of wood. You don't want a bunch of hot pieces in your house that are overheating. Okay, so you never want electrons on your circuit that are unresisted. You don't want to just let them go, okay? You always want to make sure there's either a built-in resistor. There are little pieces of equipment that are made just to slow the electrons down. They don't really do anything. They just slow the electrons down. Or if the electrons are being used, they slow down. Okay, so that's what we have.
I accidentally left like a couple minutes ago and joined back. What's the answer to number 1?
We haven't even started answering any questions, Jack, so you're all good.
Okay.
I'm going to put the switch in now and we'll talk about that. Okay, so Jack is referring to the green questions, I believe. They're green. And then there's some blue questions also. So the green questions on the document, you might hear the answer to those as I'm talking. Okay, and I'll revisit them and let anybody ask me any questions that they want in addition. So I'm going to switch back over and I'll build more of the circuit. Okay, so here's our circuit. Lights up right now as it is. What if I was to build another circuit off to the side here that goes around the light bulb? Right now, it's not doing anything because the switch is open. If I close the switch, the light bulb goes out, and then we have that situation that Jack was telling us, where the electrons are unresisted. I have it open right now, so nothing's happening. But if this is closed and I close the switch, I wouldn't want to leave it like that for too long because the electrons are unresisted and going around and around and around really fast. The evidence that the electrons, why is that? Where do the electrons go? They don't want to go through the light bulb because the light bulb is hard for them to go through. There's some resistance there. They like to go through this short circuit only when it's closed. They go through there because all the parts of this circuit are conductors. They're an easier path. The red line is the path of least resistance. That's what a short circuit is. It allows the electrons to go around the load. And then we have an unresisted circuit. Electrons going very fast could start a fire. Okay, so we probably could answer questions 1 and 2 on the document right now. What will happen if the switch is closed? We give the electrons another path around the light bulb. And that makes the electrons go fast. What do we know about circuits that don't have a load or a resistor? The electrons are going very fast. And in the simulation, we saw that that could cause a fire. They're not safe. So we've answered questions 1 and 2 in the green questions there. Okay, I'm going to open this back up, turn this off. Open system means the light bulb won't light. Okay, I have this stuff here called steel wool. You may have seen this before. Steel wool, let's see, is used to like scrub pots and pans. What it is literally like little hairs made out of metal. Okay? I can pull some of this off, twist it, and make kind of a wire out of it. Okay? With these little fibers. They're conductive, they're metal. I've done that, and I've taped it to a balloon. So this is a bunch of little tiny pieces of like metal hair all twisted together and taped to a balloon. So I've got aluminum foil conductor. The wires themselves are metal, so they're a conductor. Okay, I'm going to put them into this opening right here. Okay, before we move on to this, let's talk about question number 3 in the green. So what's different between these wires, if you will, the steel wool wires, which are little teeny, they're small, they're very teeny tiny and small, and then we have our much bigger conductors that are inside these wires. So they're both metal, but their size is very different. One is like a fireman's hose, really big, this one, and then this one is more like a garden hose. And I want you to think about the water trying to go through a fireman's hose, the wire, or the garden hose, the little pieces of steel wool. Or think about this. It's like the end of the day. The entire school is trying to go out to the buses. So everybody's out in the hallway. And you're in this really big, open, like science hallway. And then it changes to a much smaller hallway. And everyone's trying to cram into that smaller hallway and still try to go in the same direction. All of a sudden, everyone gets closer together. There's more bumping. There's more friction. Okay, if you think about that as electrons, they go from a big wire down to the small wire. It's going to cause more friction, more heating. Okay, so there's going to be some overheating on this steel wool because it's a much smaller pathway with the same amount of electrons trying to fit onto it. So far we've answered questions 1, 2, and 3 in the green questions. There are some blue questions on the next page, but they come after this next part of the demonstration. Okay, so far what we have is basically a loop, a circuit with a light bulb on it that can be closed and run the light bulb. We have this parallel circuit that has a switch, and if I close the switch, the electrons go around the light bulb. We know that when I close that switch and the electrons go around the light bulb, we're overloading, we're surging a lot more electrons out onto the circuit. They're going to go faster. Okay, so I'm going to put this in here, this balloon in here. It will light the light bulb, as you can see, because it completes the path of conductors. The light bulb is lit. Okay, this is what's called a fuse. This is a balloon fuse. So if I close this, it's as if I've created an unsafe circuit. In your house, there wouldn't be a switch that does this. It'd be like an animal chewed a wire. 2 wires are accidentally laying across each other and cause a short path that overloads electrons onto the circuit. So when I close this, the electrons are going to go around here, around the load. We're going to have too many electrons going too fast on the circuit. And maybe, uh-oh, it didn't work. Oh, maybe it's working. Can you see some smoke coming? Woo! Okay. So the balloon popped. The balloon was a point of weakness that I put there purposely. Okay? These little fibers, these little wires, I knew would overheat if there were too many electrons on the system. Okay? So now my circuit is open on purpose. It opened when the circuit became unsafe. It opened when I allowed the electrons to go around the load. It only burnt out and broke the balloon when there were too many electrons. So a fuse is something that we put in place purposely to open the system when there's too many electrons. It's designed to have something in it that will burn out on purpose if the load of electrons becomes too great. So let's look at how we can use that information to answer some questions. Okay, so you guys, we're back. To the blue questions. So on the second page, there's some blue questions. Corbett, I'll come back to that question number 3, but I really want you to think about the examples I just gave of like everyone walking down a hallway and then going into a smaller hallway and how that might cause some like bumping and friction. Okay, so we're in the blue questions, number 1. What made the balloon pop once the switch was closed? What did closing the switch do? What did it create on these red wires? They went around the red wires. There were too many electrons on the system. Why? Because the red wires allowed the electrons to go around the load. They no longer are being slowed down by the light bulb. They go out on the circuit and they're going too fast. There's too many of them going too fast around the circuit. So we have an unsafe circuit. What is a short circuit? A short circuit is when electrons are given a path around the load, around the bulb. So in this case, it was the red wires. The red wires went around the light bulb or around the load. It usually results in too many electrons going too fast. Number 3, which way would electricity rather flow, through a bulb or through the switch? Why? What is your evidence? So we saw that the bulb dimmed or went out. That's right. They like the switch better. They like the red wires and the switch because the red wires and switch are all conductors. Much easier to flow through. The light bulb is a resistor. It tries to slow the electrons down as they go through there. It's built to resist them on purpose. We use that resistance, that friction, to make the light. So they like the switch better because it's a conductor and it's the path of least resistance. So the short circuit is a path of least resistance. And our evidence that they liked it is that the light bulb went out because the electrons were going around.
I have a question.
Yep.
What was number 2's answer?
The blue tube?
Yeah.
What is a short circuit? So it's a path around the load.
Thanks.
It's usually a path of least resistance or less resistance, so the electrons like to go that way more. Most of the time, it's not on purpose. Something happens that causes a short circuit. You accidentally, while you're wiring something, you lay two wires across each other and they go a path you don't want, or an animal chews something, or something settles in your house and two wires become in contact with each other. It's not a good thing. Number 4 says, why did the bulb go out after the balloon popped? Okay, the balloon is now 2 pieces, and so is the steel wool that was laying across there. Why would that be a problem for the flow of electricity? What do we say has happened to our system or our circuit when it's torn open? So that's number 4, hints for number 4. Okay, 5 you really have to think about on your own. Like, yes, Jack, Jack's answer goes for number 4. Fuses are located in your house, in your cars, and other large circuits. Okay, I'll come back to that, Hayden. For number 5, you have to think about why would they need to be there? What are they doing? Why do we build in these pieces of equipment that are purposely going to burn out? Why do we do that? Then for number 6, I'd like you to go out on the internet and look up a definition for resistance, overload, and fuse. Okay, those words can be used in the English language in multiple ways. Make sure you maybe type in electricity fuse, electricity overload, electricity resistance, or circuit, so that you get the right kind of answer. Hayden, Jack's comment just above your answer is number 4. Okay, and if you didn't get all the answers, if you scroll down below the definitions, there's an explanation, there's a video, there's some other information that might help you find the answers that you're looking for. We've kind of talked it through here. You've watched what happened. If anyone would like to try this, of course, you can always come down during resource and do it for yourself. So you guys work for a minute. If you have a question that you're struggling with, just type it into the chat. We'll see if your classmates can help you or I can help you. When you have an answer for each thing, you have the definitions done, you've checked out it's a quick little, I think it's like a 2-minute video that explains. So we've done fuses, but fuses are kind of like not that great because you don't want just this thing in your house that breaks and then you got to go find where it is and replace it. You want something that's a little bit more efficient. So they've replaced fuses in houses with something called a circuit breaker. And if you ever know that there's a big panel in your house and you go down and you find the one that's been tripped and you just put it back and then the circuit goes back together. It closes the circuit back up. It lets you know that there was something unsafe going on. Maybe you have the dryer, the microwave, and your hair dryer all going at the same time. You're pulling too much electricity on a wire that's too small, and so it breaks the system open on purpose. But then you can go down and say, oh, okay, I won't run the hair dryer, and you go down and you flip it back over and everything starts working again. It's a little bit more efficient than having to go and replace a fuse, and maybe you don't have the fuse, and then the circuit doesn't work. So we've replaced this mechanism with a circuit breaker. So watch that video, it kind of explains that. Make sure your questions are answered, the definitions are done. When you have everything done, you may submit it to today's assignment and you will be done for the day. The only other assignment you have is to go outside and get some sun on your face and smile. Remember, at the beginning of this video, I was asking you to think of our magnet activity that we did yesterday, and I want you to think of ways that magnets are used in our everyday life. We've seen toys. Someone gave a toy example in locks and the doors. If you can give me an image or just the topic, send it to me in an email for extra credit. I guess the images would be extra credit because everybody's going to have to do something like that tomorrow for your attendance question. Please don't do it until tomorrow, though. It's attendance.